Hello, everyone. Sorry, I'm 1 minute late.
Oh,
Hi, Brennan.
hello
Okay,
everyone.
Hey, Brendan.
just getting a bunch of messages from people's note-taking things. Okay, right. Well, hello everyone. As per Litro policy, I will be starting this more officially at 5 minutes past, and same deal as last time. We're gonna have a uh, 1 hour lecture, then a break, then another 1 hour lecture. Um, Before that 5 minutes past, are there any quick questions from anyone about what's going on and what we like from work that you've done over the past week or something like that? Otherwise, we shall wait for another 2 minutes.
Yeah, Brendan, I do have a quick question.
Hmm.
I've referred to the transcripts page, and I can see
Hmm.
that you have um, uploaded each page of the slide, as I understand, but I
Um,
actually couldn't see the recording. The voice recording. Would you be able to
the
just
voice recording,
yeah.
not video recording, voice recording.
Oh, or either or.
So you're talking about the lectures or the labs?
Well, I was specifically referring to the lectures, but in this case, both.
Hmm. Okay. Um, I will share my screen and show everyone and double check that it's there how to get to the lectures because I think
Great.
that's good.
Thanks,
All right,
Brendan.
so let's go here. So as always, we're going to start from the home of the LMS page.
Hmm.
And then we have the live sessions tab, which lists, let me show you what you're going to see. I keep forgetting. That's what you see. Um, You have the live sessions, and you have the links to the live sessions, and then at the bottom we have recordings and resources.
Yes.
So then we have links here to the different sessions. So the first one is the link to the lecture, and it has a passcode. So I'm going to copy that, click the link, and just so actually let's open that in a new private window so it doesn't have any of my login details. All right. So this is what you should get. This is what anyone should get.
Uh-huh.
I paste in the passcode and I click watch recording, and then it should come up with the video. And we have the video. Now you
Okay.
notice that I mentioned the lecture officially starts at 43 minutes 25 into the recording because the recording technically starts whenever the first person enters the room. So we want to start through at 43, which one was it? 43:25.
I see. Okay.
43:25. So we can watch a lecture in the lecture now.
The
You know,
Matrix.
the matrix, yeah. So that's how you get to the lecture from LMS, and everyone should be able to access that with the passcode um, you copy and paste.
Recordings and resources. I see. Okay.
Are the slides there as well, or what? That you used
Um, Actually, have I uploaded the slides? Hold on, let me check.
from last week? I just realized now. Yeah.
Yes, I have not uploaded the slides. I will do that during the break. For
Okay.
now.
Okay. Because admittedly, what I did now I know what I've done wrong was
Hmm.
because there's actually a transcripts tab on the navigation bar,
Oh, I see. Yes.
and it's right at the bottom there.
Yes.
So I thought that that was the purpose of that transcripts page.
No, it seems to be a references, not transcripts. I've just opened it up.
Yeah, and that's why I was thinking, oh, you've kind of given us sort of the references and figures, but not the actual
Yes.
recordings.
Yes, I don't know
So,
why that's called transcripts. It wasn't my decision.
oh, that's very misleading.
Yes, it is misleading. I will probably talk to Josh about that one.
Okay, all right. So,
Yes, that should be
just
called,
to
that should definitely be
confirm,
called references, not transcripts on LMS. Yeah.
got you. Okay.
All
So
right.
going forward,
Mm-hmm.
it's just exactly as you described. It's going to
Yes.
be in
And
live sessions down the bottom there with recordings and resources.
yes, I will be uploading the slides to that same location.
Okay, got you.
Yeah.
Because yeah, obviously I was
So the
looking for those
recordings
and
and the
couldn't find
slides will
them.
be in, yes. Sorry about the slides. Managing several instances and I've uploaded it to the other instances. I forgot about this instance. I apologize.
Thanks, Brendan.
So I'll upload that during the break. For now, it is time for the lecture. So let us let me get that ready and then we can share the desktop. Okay. Can you see my screen?
Yep.
Excellent. Can I draw? I can. That's good. Are you getting a any graphical issues with the laser pointer? Last time, okay. Last time we had problems with that. Anyway, it's fine. Okay. Welcome to lecture 3 for the Artificial Intelligence Fundamentals or subject. In this, sorry, in last week's lecture, we talked a bit about data. We talked about what data looks like in a computer, how it's stored, and how it's related to one another. And in this week's lecture, we're going to talk about how data is used to produce machine learning models.
Excuse me, this is week 2, so lecture 3 or lecture 2? This is
This
week
is,
2, no?
we do 2 lectures per week. So it's 2 hour lecture, 2 separate lectures.
Right, okay.
That's how we're numbering them for consistency.
So this is module 2 or module 1? Module
This is
3?
module 2. Module 2. Sorry
Ah,
for the confusion. This is module 2. The first lecture of module 2 is lecture 3. All right. So when we're talking about machine learning, um, there's a few key ingredients that you should be aware of. You should know what they are, why they're there, um, and how they fit together. So this lecture will be going through those key ingredients. So by the end of this module, and that's basically it, we'll go through those ingredients, and then we're going to have some examples of it in action so you can get a better idea of what those ingredients are. So at the end of this module, you should be able to identify and explain those key ingredients, which are not actually listed here. It's the data, the model, and then a loss function and a optimization algorithm. And these are powered by the input and the output of the model. And as a side, another thing you should be able to do is you should be able to distinguish between regression and classification tasks. You should know what they are and when you're using them. Check. See. Okay. Um, so let's talk about those ingredients. We're going to start by talking about models. By the way, can you see the top of the screen? Is the text being cut off at all? Because I noticed that the sharing bar is there.
No, it's fine.
Okay. You're all good? Okay, cool. So we're going to be talking about models. In a broad sense, we make models in our brains all the time. This is, in fact, how we go through life. When we're walking along, we're going to predict whether somebody's going to walk in front of us. If they're walking at a particular angle, maybe they'll cut us off. If we're driving, same thing. We're predicting where cars are going. We're thinking about the future. Should I take an umbrella today when I go outside? Is this email spam? Which queue at the grocery store is moving the fastest? We see things in the world and we make a mental model of what's going to happen in the future, and then we make decisions based off of that. In order to make these models in our heads, we have to observe the world, right? So we have to think about what information are we using to make our mental predictions, our mental models of how the world works? What are we using to power those models? Because if we want a machine to be able to predict the future, like we can predict the future, or better than we can predict the future, then we're going to have to think about what information the machine needs as well. So then what is machine learning? Machine learning can be described as the process by which we make a computer produce a model from data. So when we're making our personal models, we use a lot of information about the world. And when a computer makes a model, it is similarly using information about the world. In the terms of machine learning, like the language of machine learning, a model is just anything that transforms inputs into outputs, or more precisely, predictions of the future of a thing. So, for example, a machine learning model would be, and of course, sorry, between humans and machines, we have different things that we're sort of better at, right? Things that are more number crunchy types of models are better for machine learning models. So, for example, if we wanted to use calories eaten today to predict someone's body weight, those are very number-based things, and that's where machine learning will give you a better result than just sort of us eyeballing it, right? So we have many things that are good for numbers, right? Number of calories is a number we can use to predict body weight, which is a number. Time of day and temperature can be represented as numbers, and that'll can be used to predict the amount of electricity usage in an hour, and that's also a number. In this lecture, we're going to be going through an example of different kinds of information from a house that can be represented as numbers in order to predict a house price, which is a number. And so machine learning uses data, like we saw in last week's lecture, tabular, image, or text data, and it uses those numbers to predict another number. And in order to do this, in some sense, that model is representing reality inside of that model. Now, that sounds fairly complicated. That's something that we do all the time, and it's kind of difficult to explain how we do that, right? Between machines and computers, so machines and humans, machines and humans, um, when we're talking about building a model, there's a lot that's the same. It's all based on data. It's all about training. And we can think of two different situations. We can think about all of the information that we've collected over years of our life up until the point at which we need to do a task, and then the information that we require at the time that we are doing the task. So if we're looking at uh, trying to navigate a busy street, we've all walked down streets hundreds of thousands of times, and so we've seen how people move and we're used to that. And all of our past experience, that forms training data for our own mental model so that when we're walking down the street, we can see how people are moving and we can plan how we're going to move so that we don't bump into them. So these are the two times that we're going to talk about. There's training time and inference time. The first majority of what we're going to be talking about is all going to be about the training, how we're going to train a model using the data that we have. Now I'm going to take those two things I just talked about. The previous slide, where I talked about how it's number crunchy and what is even a model, and training a model. How do we make a model? This is all about making a model. So in this slide, let's look at the simplest possible number crunching model that we can have. This is called a linear regression model. It is a formula. It is a very simple formula. And this is a model maybe for predicting electricity usage. It could be the usage is going to be modeled as is equal to some value A times the time of day in hours, plus some value B times the temperature, plus some value C. In this model, we would say that the time and the temperature are inputs to the model. The usage is the prediction or output to the model of the model. And these some value A, some value B, some value C are parameters of the model. So if we want to predict usage well, the goal of machine learning would be to adjust these values, this A, this B, this C, to maybe 1.2, 3.7, 0.9, right? We want to adjust these values and we can change those values so that we get a good model. Okay? So our goal is to make a good model, right? Obviously, we can all make models, but we want to make a good model. And a machine learning model is defined as this number thing, this number crunching, this equation. And the process of machine learning is just choosing these values of A, B, and C. So Ahmed, you have your hand up?
Yeah,
What do you want to
doctor, I
ask?
have a question.
Yes.
How like to identify the parameter like that are relevant to each case, and is there like any rule like define minimum number of parameter to be used to predict?
So the this is this is called your model, right? So if you choose a different set of parameters, that is you choosing a different model. There are common types of model, which we will cover in the coming lectures, including this one. This model is called linear regression. And if you only, basically, you have one parameter per input in linear regression. So if you're doing linear regression, you have one parameter per input. And that's just how it is. That's always how it is. Whenever you are doing that, whenever you are making a linear regression model, you just count up the number of inputs, and that tells you how many parameters. It's the number of inputs plus one because you have this extra C on the end. When we look at neural networks or we look at regression trees, the number of parameters is different. And there's different guidelines for different models on exactly how to get the how to choose the number of parameters. That is for most models, that's a free choice, and it's something that you experiment with as you go through. And we'll talk about experimenting with the number of parameters. Good question. Maury, you have a question. You have put your hand up.
Yes, I do have a question in regards, like I understand that A relates to time, B relates to temperature, but
Or is multiplied to,
C
yes.
here, yeah, C here doesn't makes sense because it's on its own. So yeah,
Okay.
that's
So in this case, C would represent a baseline usage that is not dependent on time or temperature. So if you have a light that is always on, or your fridge is always on. It doesn't matter what time of day, what temperature it is. Well, maybe fridge might adjust a bit, but there's going to be a few things that are just always being used, right? There's some sort of base load that's always going to go happen. That's what the C represents. Does that make sense?
yes, thank you.
Okay, cool. All right, let's move on. Rupali, I see your question. We will cover that momentarily. Um, right, so those four ingredients that we want you to know about. Those four ingredients are how we create a good model. One of them is data. We've talked about data in previous lecture, and we've just talked about it here. These are your previous experiences that the model has to have seen in order to know what to do. You have a model. It might be a linear regression formula, like we just saw, or it might be a multi-layer perceptron, which we'll look at in the lab. And then we have these other two things, which we're going to talk about, called a loss function and optimization algorithm. So this is a diagram that shows the process of machine learning, the process of obtaining the parameters for the model. That's what machine learning is. We are creating a model. What is a model? A model is basically a formula that uses parameters. And so we're trying to find those values. That's the whole thing of machine learning. This is what we're trying to do. So if we have our training data set, this is our data that we're going to use to find good values for those parameters. What we're going to do is we're going to look at maybe one row of that data set. We're going to take the input values, we're going to put it through the model, we're going to produce some output, and then we're going to use that output to adjust the parameters. When we create a model, when we start with a model, usually the parameters are sort of random values. Well, for multi-layer perceptron, they are random values. For deep learning, they are random values. Technically, for the linear regression, we don't need to start with random values. We can just find the values straight away. Um, but the general process is the same. Whatever parameters we have for the model, given some inputs, we can calculate some outputs. And if we calculate outputs, we need to be able to measure how correct those outputs are to continue. So for example, I'm going backwards now. Actually, we'll look here. So in order to train this linear regression model, we would need to have a data set which contains three values for every row. So we're going to look at a table, and each row has three values, there's three columns. It has a time, it has a temperature, and it has a usage. So for every time of day and every temperature, there is a recorded usage in the table. We require that in order to adjust the parameters so that the model is good. And so when we're training a model, we take the input columns, the time of day, the temperature, we make a prediction, making the electricity usage, and then we compare that output, that predicted output, with the known answer that we have from our training data set. And the difference between these is calculated using a loss function, and the result of that calculation is called the error. That's how wrong is the model. So for our loss function, we need it to tell us how wrong is the model. And then the last step is that there's some optimization algorithm that looks at how wrong is this model, right? And it says, okay, it's wrong of 5, or whatever number. It's just an arbitrary number. And based on how wrong it is and how wrong it has been in the past, the optimization algorithm will choose new values for the parameters, better values, values for the parameters so that the output will be more similar to the known example, the known answer. And so for the rest of this lecture, we're going to be talking through that process in more detail so you can see it. Okay? So machine learning is a process of optimizing the optimization algorithm, optimizing a model, which is optimizing the parameters of a model by minimizing the loss function using data. And so by the end of this lecture, you should know what that sentence means. At the moment, it's going to be a bit hazy because you don't know exactly what that is. But at the end of the lecture, we hope that you know what that means. Okay? So let's talk about those loss functions. We mean measuring how wrong. Okay? If we want to improve a model, we need to know how wrong it is so that we can say that the loss, so that how wrong it is goes down, right? If we can have a number that tells us how wrong the model is, then all we need to do to define how wrong it is have some sort of function that when that function is zero, the model is completely correct. And any other positive value means that the model is incorrect. And as that number of how wrong it is gets bigger, the model is more wrong. Let's look at some numbers, maybe a bit easier. Let's say we're going to sell a house for $800,000. But before we sold the house, we had three models that had been trained. We had three models that had been trained, and we had three models that had been trained to predict the house, and we had asked those models how much will this house sell for. They have access to some information about the house, what the floor area is, that sort of stuff. And then they're going to use that information to predict how much the house should sell for. And we have three different models, and they make three different predictions. These are just hypothetical, it's not real models, but if these three models made these three different predictions, we can measure how wrong each of those models are. The first model, maybe we would say that's $200,000 wrong. It is incorrect by $200,000. The second model is wrong by $790,000, which is bigger. And the third model is also wrong, as same as the first model, by $200,000. So if we want to represent this idea of wrongness by $200,000, but it doesn't matter whether it's up or down, we need to use a specific mathematical operation called the absolute value. So, and a subtraction. So let's have a look. I think we've got the formula here. We want to measure the absolute error, is what it's called. We take the value that the model predicted, y hat, and we subtract that from the known price, the known value, and then we take the absolute value. So if it's negative, absolute just means if it's negative, we take the positive of that value. So if it's negative 200,000, then when we take the absolute value, we have 200,000 positive. Okay? And this satisfies what we needed from a loss function. If y hat is exactly equal to y, which is that if the prediction of your model is exactly equal to the known value, then this formula becomes zero. Then, as the prediction y hat becomes increasingly different to the value y, the absolute error becomes bigger. So we bring it back to that diagram before. I'm just going to quickly go back to it. This loss function informs the optimization algorithm by telling it how far away from perfect are we with the error. How incorrect are we? What's the error here in a number? Now, often we have many examples. not just one. So usually when we talk about absolute error or any kind of error, we will take the average over every example. So in this case, if we have a data set containing 4 examples or 4 rows in a table, then we would take an average over all of their mean, that should be mean absolute error. Sorry, that's a typo there. It should be a mean absolute error, not average error, mean absolute error. Take an average over that, and that tells us how well does this model do on our data set, right? So previously we've just been looking one item at a time. This is absolute error. It's got this much error for one row. This mean absolute error tells us how well does the model do overall. So in this case, we would see that model 1 has an average absolute error, this mean absolute error of 60, and so does model 3. And model 2 has a mean absolute error of 65. So model 1 and 3 seem to be about as good as each other, and model 2 seems to be a bit worse. I'll talk about why seems to is important in the latter half of this lecture. Or next lecture, perhaps. Right, so that's the loss function. We're measuring how wrong is the model. How wrong is the prediction of the model. The other ingredient that we need to talk about is the optimization algorithm. Remember that machine learning is a process of optimizing model parameters by minimizing a loss function using data. The entire behavior of the model is controlled entirely by these values, A, B, and C in this case. These are the parameters. We don't know what those are going to be, but the optimization algorithm is a algorithm to choose those values so that this loss function, this mean absolute error, is the lowest value we can possibly make it. We won't be talking about exactly how these work. That is fairly complicated. That is stuff that you will learn in later study, further study of machine learning and deep learning. All we want you to know is there is such a thing as an optimization algorithm. Optimization algorithms choose the parameters of the model, and they choose the parameters so that the loss function is at the minimum we can make it. That's all it is. And the other thing is optimization algorithms often have names. And so where we can name them, we'll name them. That allows you to look them up if you want to. You can see how they work, but we're not requiring you to know how those optimization algorithms work. So those are the 4 key ingredients that you will find in machine learning basically everywhere. That covers, and I'm just going to go up to the previous slide. What we've just been talking about is machine learning. Remember at the beginning, we talked about how artificial intelligence is kind of an umbrella term that covers many things. Inside of artificial intelligence, we have machine learning, which is one kind of artificial intelligence. And we've just talked about what machine learning means. It means we're optimizing the parameters of a model using data. And then inside of machine learning, there is deep learning. That is a kind of machine learning, which means that it has these same 4 ingredients, but it has a specific set of loss functions, models, and optimization algorithms that are specific to that kind of machine learning. Okay. So let's have a look at this with some examples, right? Let's identify those pieces in some kind of toy examples. So in the module notes and in here, we're going to talk about this house price data set. It's just a made up data set of 11 houses with 3 columns for prediction and one column for the target that we want our model to make. So there's four columns of data, three are for input, one is for output. So we have the size, the number of rooms in the suburb. These are the three columns here, and then the price is what we're trying to predict. So we look at this house. We look at these houses. We could look at this data and make some predictions about what is the like how important is each of these values, and if we saw a new house in one of these locations with a size and a number of rooms, we also could make a prediction, right? So if we want to think about how the machine learning model using numbers like a linear regression model would do it, before that, we can think about it as how would we do it? How would we do it? We would look at it. We would look at some of these prices and the floor sizes in the rooms, and we try to make some patterns. We try to figure out some patterns. So if we look at just the low number of rooms, 1 room, 2 room, 2 room. Okay, so those prices, when we're looking at it, those prices seem to be lower than the places with more rooms. So that's a pattern that we can see in the data. And if we wanted a machine learning model to work on this data, we would hope that the machine learning model would also pick up on that kind of pattern, where the number of rooms seems to have a positive correlation with the price. If you have more rooms, it should be more price. New house comes in, if it has 4 rooms, we would expect it to be much more than $600,000. Made up numbers. So, for understanding this, understanding what the model is doing when it has this equation, it's nice to be able to visualize things. So we're actually going to take a subset of this data. Instead of looking at the full 3 columns to start with, we're just going to look at the floor area, okay? And we're going to define a model, a 1D model, that uses one input, a simple linear regression model on that. We're going to define it with A times the floor area plus D, okay? And that means that there's 2 parameters that we have to find. And we could just figure out, we could just like make a guess about what the value should be. And maybe if you play around with it a bit, you could end up with A is equal to 5 and D is equal to 60. And you might end up with this equation. Now you might, this is sort of maths methods or calculus sort of level, sort of high school calculus level sort of stuff. But if you haven't seen it, I just want to talk this through just a moment to make sure that we're all on the same page about what this is doing, what this line is representing. This formula defines this line. It says that when x1, the floor area, is 0, the price should be 60. Now, that's not a real thing that would happen in the real world, but maths doesn't touch the real world in the same way that we do. It's just numbers. And so we think of this as what's called the y-intercept. That's where, if we extend this line out to 0 area, which couldn't happen in reality, but we can do it in maths, it would cross this line here at about this point, 60. And this value 5 tells us the slope of the line. It tells us for every unit area, every 1 square meter area, how much does the price go up? So in this case, it says the price goes up by 5. So we can see here, 1 meter squared goes up by 5. So 25 meters squared should go up by $125,000. And that's every 25, it goes up by 125,000. That's what a linear model means. Doesn't matter whether it's this 25 or that 25 meters squared. Every single 25 meter squared that the area goes up, this model predicts that the house price will go up by $125,000. Okay, so that's a linear model. This is a 1D linear model. How correct is this model? It looks pretty correct, but we want to have a number so that we can optimize, right? We want to have a loss function that can tell us how right it is. And for linear regression, the number that we use to optimize is the squared error. So we previously looked at the absolute error, where we had we took the minus and we took the absolute of the result. For linear regression, just by convention, we use the squared error. Instead of absolute, we take the square of it. It functions mostly the same in the sense that 0 still is perfect. In a sense, perfect. It's perfectly predicted the training data. And instead of it just being the absolute value, we take the square of it, which still means that it's always positive, right? Which is the same thing that the absolute has. So the bigger the squared error, the worse the model is. So in this case, when we take the squared error, we end up with 5,575. But this was just a guess. This was just choosing A and D from eyeball, right? This looks pretty good, but it's not necessarily the best. What is the best? Well, we can run an algorithm to find it. And for linear regression, the algorithm that we talk about is ordinary least squares. And when we run ordinary least squares, we find the values 4.6 and 93. Give me 1 second. I just need to double check. Yeah, okay, cool. Yep. So linear regression, sorry, this is ordinary least squares to find those values. Remember, we talked about the optimization algorithm. The purpose of the optimization algorithm is to find the parameter, find the values for the parameters so that the prediction is as close as possible to the true values. And so when we run ordinary least squares, we get these values for A and D, and we can plot that, and it looks very similar, just a little bit different, right? You can see that it does a little bit better on this bottom one, a little bit worse, does a little bit better here, right? And when we add up all of the errors over the whole data set, turns out that this one does better. How do we know that it does better than our guess? Because we measure the loss. We go sum of the squared error. So the squared error on each of these, what is the sum of all of them? Well, this is 6,969, which is smaller than 857. So it seems like this model where we've optimized this is better. In fact, for linear regression, ordinary least squares will find a value for A and D such that the sum of the squared error is the smallest it can possibly be using this data. Now, the data might be wrong, and so that might not get you the best model, but for the data that you have, ordinary least squares is guaranteed to find an A and a D value that will give you the smallest possible sum of the squared error. Okay. So those 4 ingredients, it's useful whenever we're looking at a machine learning algorithm. We want to identify those 4 ingredients in the machine learning algorithm. So in this case, the data was the house price data, the table that I showed you before. The model was a very simple mathematical 1D linear regression model. A times X plus D. The loss function in this case was sum of squared error, which is the loss function you always use for linear regression. And the optimization algorithm is an algorithm called ordinary least squares. This is just the name of it, so you can look up ordinary least squares somewhere else if you wanted to find out how it works. How does ordinary least squares work? I think it's a bit mathy, and I don't really want to get into it. But the point is that it is finding values for A and D. It is calculating values. It's not just finding, it's calculating. It's all maths, right? So it's calculating what value of A and what value of D gives us the sum of the smallest sum of squared error. Because if it's all maths, you can all plug that into formulas to find out what value gives you the lowest sum of squared errors. So that's one input. Of course, we had a table that had 3 columns. We did one input because we can graph that easily. But it has 3 columns, so we won't be able to graph it very easily, okay? So previously we looked at the price versus the area, and we could plot those points on that graph, and then the model was a line, was just a single line on that graph. When we're using multiple inputs, then our data isn't just one value compared to another value. It's one value compared to the output, and another value compared to the output, and another value compared to the output. And so this makes it actually a bit hard to visualize. In the lab, we're going to go through some visualizations as we go up in dimensions. Obviously, in this case, it would be a 4-dimensional graph, which we cannot draw. But in the lab, you'll have a look at 2D graph versus a 3D graph and hopefully get some intuition about what that sort of looks like. In any case, if we have multiple input parameters, these are different multiple inputs columns. These are different dimensions along which the model can try to fit the data better. And so this should give us a better result if we have more information about each house in order to make the prediction about the price. Something you'll notice here is that area is a number between 0 and 200 in this graph, and number of rooms is a number, which is value between 0 and 5 in this graph. But we've also plotted suburb, which is not really a number. And importantly, there's something about this that is not generally, something about numbers that is not generally the case for categorical data, right? So we have 4 different categories of stuff here. I think that's really important about it is that for numbers, these are ordered, strictly ordered. 1 is strictly less than 2. And if you times 1 by the value 2, you'll get to 2. If you add 1 and 2 together, you'll get 3. These are the properties of numbers on a number line. But for the suburbs, you can't ever say, okay, if you add Brookville to Oakview, you're going to get Lakeside, right? That wouldn't make any sense. So we can't represent the suburb as just a number on a number line. We have to do something a bit different. And if you think about it, area and rooms are kind of incompatible in the same way that Brookville and Oakview are incompatible. If something is in Brookville and if a house is in Brookville and another house is in Oakview, there's no strict numerical relationship that tells you how to translate between them. Same way that there's no way that you can translate between area and number of rooms directly. Maybe you can make a prediction, but it's not strictly known. So when you have categorical values, typically what we will do, almost always, what we'll do is we'll give each option its own column. So instead of there actually being 3 columns, when we do this transformation on our data to give each suburb its own column, we actually have 1, 2, 3, 4, 5, 6 input columns. And the way that we turn these suburbs, these basically words, into numbers for a computer is we use something called one-hot encoding or a one-hot embedding as well. These are interchangeable terms. A one-hot encoding, a one-hot embedding, is defined like this. If we have those 4 new columns that we've added, if there is a house that is in, and they correspond, sorry, each of the columns correspond to those different categories that we could have had. So this one's the Brookville category, this is the Oakview category, this is the Lakeside category, this is the Hillcrest category. If the house was in Brookville, then we put a 1 in the Brookville column and a 0 in the other columns. If the house was in Oakview, we put a 1 in the Oakview column and a 0 in the other columns. And what we end up with is each row has 3 zeros and 1 1. If we had 10 suburbs, it would be 9 zeros and 1 1. This is a one-hot encoding. There is one column that is hot. It is the one that has been selected as the value. And this is how we can turn this categorical data into numbers to put it into a formula. Because now we can create the same deal. We can create a linear regression model with all of those columns, and it works the same way as before. We have the value in the column multiplied by some value, some parameter of the model. This is the first column, the floor area. This is the second column. This is the number of rooms. This is the third column. This is whether the house is in Brookville. And then that's going to be worth something. That's going to be given a value to the C for Brookville, C for Oakview, C for Lakeside. And so we have now 1, 2, 3, 4, 5, 6, 7 different parameters for this linear regression model using this table of data that has many columns. And so a linear regression model on this will have a value for each of them. It'll find a value for each of these parameters. And just because it's in 7 dimensions versus 1 dimension or 2 dimensions as it was previously, the maths turns out to be exactly the same. You actually don't have to do anything different. It's just we can't visualize it as well. And this pattern sort of repeats as we go through. Oh my. We have run out of time. All right. I'll be spending 5 minutes to go through these ones. I think it was important to go through those things. I'm not sad that we took a while on them. So now we're going to talk about a different model, right? We have the linear regression model. So we have the linear regression model before. We looked at that. This is just a formula. And then we're going to look at 2 other models that we typically use, or we could use. We can have regression trees, and we can have simple multi-layer perceptrons, which are simple neural networks. So these are the 2 models that we're going to look at.
Brandon, sorry to interrupt. Just back to that linear regression. How,
Yes.
like all of that numbers, like 2.73, all of that numbers, is that given to us? Is it all the parameters?
Those are the parameters which were identified by ordinary least squares. So
Okay.
ordinary least squares finds the values of the parameters.
Okay.
And these are the parameters that ordinary least squares found by
And we
minimizing
don't
the
need to
loss.
know how to calculate that?
You don't need to know how to calculate that, no.
Okay. Okay,
Yeah.
cool.
And
What about
so
how to calculate the SSE?
you do need to know
SS
how to calculate the sum of the squared errors, yes.
Yeah.
And that is the formula that we
Yeah,
looked
that
at.
was y minus y, whatever. Yeah.
That
Yeah,
is
yeah,
the
yeah.
the value minus the prediction squared, and you sum that over all of the data.
Yeah. Okay, cool.
All right, so regression trees. This is a different kind of model, and we're not going to have a formula for this one. We're just going to look at what it could be, right? Or look at well, yeah, so instead of it being a formula, it's actually more like a bit of code, right? It's a bunch of if-then statements, right? In the previous previous lecture, we talked about trees, and so a regression tree is just a tree where you're making a decision at each point, and then the result is a number. So it's just a collection of sort of true false statements. Is it, in this case, this is a model of the price where we start here and we say, is the floor area greater than 100 meters squared? Is it less than 100 meters squared? So is it greater than? True. Is it less? Is it not greater than? That's false. We go here. And so if we want to make a prediction for the house price, we can follow the nodes and connections on this tree to come up with a prediction. Now, regression trees are a machine learning model. So when we're making these models, we don't hand decide. We don't figure out what these values are. We let the computer figure it out. In the same way that we let the computer figure out the parameters of linear regression of A, B, C, D, we let the computer figure out where should the split points be, what should the questions be. We just want it to be able to find values that get a sums of the squared error that is very low for this data. And so if we train a regression tree on this data, we get this tree on the left, which is really just a partition on the space we can see on the right. Because this tree, if you follow it to a leaf node, the end of it, it doesn't matter what the floor area actually is. No matter if you've gotten to this part of the tree, this last node at the top. Sorry, I think you can. Let me just make sure. We've got spotlight. So this part up here, this 400. We get to this node, then the price is 420,000. That's the prediction of this model. And so in this visualization over on the side, we have different areas of the graph where the line is the prediction of the model, and each of the different colors is just a different sort of end point of following the tree. Okay. Again, we're going to talk about how we get these values, but we can think of where it splits and what the question is, whether it's above or below some value. Those are the parameters which the optimization algorithm has found. Okay. Now, for this case, the sum of the squared error is 9,080. That is much worse than the multi-dimensional linear regression, which got a sum of the squared error of 2,787. So this regression tree seems to be a lot worse. Why would we ever use a regression tree? Well, it's because some data is not strictly linear. We saw this data and it kind of looks pretty linear. As the floor area increases, the price goes up, and that is sort of a consistent thing that always is true. For all the data we have, so long as the area is increasing, the price is going up. However, that's not always the case. Not every relationship is that simple linear relationship. So we have another data set we're looking at here where linear regression does a lot worse. You can see some hypothetical data set where we have a meal price versus a meal size, and your cheap meals are not very big, and then you get reasonably big ones, and then your fancy meals, which are also not very big, but they cost a lot. So for this data set, grouping them into sort of categories to give a regression value makes more sense and matches the underlying data much better than linear regression could. So the key lesson I want you to get from this is that your model should match the distribution of your underlying data. Your model should look like what your data is. Should look like what your data is. So if your data is linear, then a linear regression makes sense to use and should be used and is preferable to use. If your data looks like it's in sort of separate groups and sort of more complicated, you should use something that groups them up. Or, here's the cool thing. Here's what we're all building to. Instead, maybe you can just use a neural network. The key thing that neural networks claim to be able to do, the thing that they want to be able to do, the things that they mathematically have been shown that they can technically do, is that they can match the underlying data for any data, provided there is enough parameters in the neural network to be able to do that. Okay. Now, a neural network, we're quite a bit over. I'm just going to quickly talk about the model for a neural network. We draw it like this. We draw it with some circles and some lines, and some circles and some lines. And this is a representation of a mathematical function, just like for linear regression, except it's a little bit more complicated. In fact, it could be described as linear regression plus another thing plus linear regression plus another thing. This is based on linear regression, but it's just more complicated. We're doing some more things on top. And so the formula for a neural network can be described like this, where you have sort of a linear regression thing going on here. You have a function on that linear regression, and then you have another linear regression. So this is a two-layer neural network because there's two layers of that linear regression going on. But there's also another aspect to this, that linear regression. Remember how we could have multiple, we had to have multiple parameters for each of the inputs? Same deal here. This B, actually it's a group of parameters. We're just simplifying the formula so that we can see what it looks like. If that didn't make sense, don't worry too much. You're not going to be tested on that. All I want you to realize is that a neural network, a two-layer neural network, is a fairly simple mathematical formula that has a lot of similarities with linear regression. And when we optimize this model, remember, optimizing a model is defined as choosing the values for the parameters. Optimizing a neural network is choosing the values for these groups of parameters. And the name for the optimization algorithm is actually, there's two names because there's two separate steps. There's stochastic gradient descent, SGD, and backpropagation. It's not really playing here. There's a little animation in the course notes where you can see a model is matching the data. And point is that neural networks, because it's more complicated than linear regression, you can't do it in one step. You have to iteratively update the parameters so that you get a lower loss, a lower loss, a lower loss. And so this would play an animation, I can bring it up later, where the line starts really bad. As you can see, it's a bad line, but it improves over time and sort of finds a good point. The last step, I recognize
I
we're
just
over
ask
time.
one question?
I will ask you to hold the question until I finish this one more slide, and then we'll have a break and you can ask the question during the break. We are
Okay,
over time.
all right.
I just want to
Thank
keep
you.
the time. Sorry. The last thing is talking about regression versus classification. So we've just been talking about regression. We've been talking about predicting a number. We've been talking about predicting a house price. So that's a number. That we want to compare that to another kind of task called classification, where we predict a category, a label. So maybe we could predict whether an email is spam or not spam. It's a hard boundary. It either is spam or it is not spam. Or this is a picture of a cat or it's a picture of a dog. Or it's in Oakview or it's in Hillcrest. These are mutually exclusive categories, usually mutually exclusive. Okay, these are two different kinds of tasks. We've only been talking about regression. Talking about classification, it's the same basic idea, but it has a few more complications because it's not just numbers. We can't just write a function like this for classification. We have to do a little bit extra. It's still the same idea underneath. We have to do a little bit extra. We do a little extra step at the end. I just don't want to talk about it in the lecture because it complicates it a bit more. All right, that's the end. So in summary, machine learning is a process of optimizing model parameters by minimizing a loss function, trying to make a loss function equal to zero or as close to it as we can, and it's using data. So it's machine learning using data. The four ingredients that we use are the data, the model, which is often just a mathematical formula. We use the loss function, which is another mathematical formula to calculate how wrong the model is, and the optimization algorithm, which selects the parameters for the model, which minimizes the loss. The most common machine learning tasks we will talk about are regression and classification. Regression being predicting a number, classification predicting a category. All right, that's the end of the lecture. I apologize, we've gone a bit over. We will have a 5-minute break now, and I will take the question that I didn't catch your name. I didn't know who
Oh,
was
yeah,
asking.
it's Matthew.
Hi, Matthew. Okay, so we'll meet back at 12 minutes past. So we'll meet back at 12 minutes past. I will not start until 12 minutes past. You can go have a drink, whatever, and now I'll answer the question. Okay, Matthew, what was your question?
Oh, yeah, it was just the neural network formula. On that page, it didn't say what the sigma represents.
I did not say what sigma represents. It is one of those complications that I don't want to go into detail for everyone. I'm happy to describe it for you here, but it's kind of, I think it complicates it for people.
This
So
is the activation function, this one sigma,
it is an activation function,
like
also
Oh,
ReLU,
right.
right?
Okay. Yeah.
also known as a nonlinearity. There are different functions. There are ReLU, tanh, sigmoid. These are different functions that can exist, and that's one of the things that you can choose about the network. You can choose which of these to use. They're just a one value input, one value output function.
No, that's fine. That makes sense because I know what an activation function is. So yeah, that's
Okay, you know what
thank
that is.
you.
Okay. Yeah,
Hi.
there's a mix of how much people know. Sorry.
I
Yes.
would like to ask one.
Yes. What's up?
Yeah, in the first loss function in linear regression, we use MAE, and the second square error, we use SSE. Why don't we use mean square error instead use sum of the square error?
Convention, mostly. So linear regression. So if you minimize the sum of squared error, if you think about it for a moment, you can see that that's equivalent to minimizing the mean of the squared error, right?
Yeah.
It will give you the same answer, right? Talking about the sum of the squared error is links linear regression to a lot of the more complicated mathematics that underlies machine learning. They often talk about the sum of the squared error because it's especially related to the standard deviation and variance of your data set, if you know what those are.
Yep.
The sum of the squared error is actually more aligned with those values than the mean of
I
the squared
see.
error.
I
So
see.
when we talk about linear regression, it's just sort of a convention that we talk about the sum of the squared error.
Okay. Yeah. Thank you.
No problem. Oh, I will have to too.
Hi, Brandon. How are you?
Hi, Tristan. All
Hi,
right.
can I please ask a question about train and test split?
Would you mind holding the question until next lecture, where we're like after
So
the
you'll be
break?
covered there.
We'll be
That's
covering the
great.
train and test split. Yes, that's right.
All right. Thank you.
Sure.
Brandon, just quick question. I can see you have called out the due date as 24th of July, but if you have the extension, then we can basically submit it by 27th. Is
That
that
is
correct?
correct. Yes.
Yeah.
If you have this is the official due date, but you can also have the 3-day extension. If you have the 3-day extension, it will be Monday the 27th.
Yeah, and there is no penalty for the extension.
No, there's no penalty for the extension.
Okay, all right.
Just if you
Thanks.
feel like you need more time, you put yourself in for the extension.
Thank you.
Well, I just regarding the extension, I applied for the extension when the due date was this Friday. So what will happen to my extension? There's already used the extension option.
If you have the extension, yours is due on the Monday, the 27th. That there is no other way for it to be.
Okay.
The due date is Friday, and the extension makes your due date, like your personal due date, on the Monday.
But if I had applied today, it would have been Wednesday or Thursday, or is it? Oh, sorry.
No.
So the
There is no change. This is no change to how it has been.
Oh, okay. So they haven't changed.
There has been no change. There has been no change.
Okay. No worries.
Yeah.
So,
If I get an extension to Monday, but I can still submit on Sunday, no?
Yes, you can submit on Sunday. You can, in fact, I think you should be able to. Oh no, for this one you can't submit late. You can't submit this one late. Yes, so you can submit earlier. You can submit today if you want to.
Okay.
But if it's the due date is on the Monday.
and Monday is like till before midnight, or just
Yes.
end of. Yeah.
Yes. So it's plus 3 days. Hold on. So it goes to Saturday. So we're adding day by day. From Friday's 11:59 to Saturday is 1 day, to Sunday is 2 days, to Monday's 11:59 is 3 days. So 3-day extension gets you to 11:59 on Monday.
Thanks.
One question regarding the recordings.
Yes.
So I'm looking at the recordings and resources. So for week 1, it shows, and so this is exactly where the recordings can be found, right? So if I need to refer back to any documents or any labs.
Hold on, I showed at the beginning. I will show you again. Oh, sorry, I'll show again. You maybe weren't here at the beginning. That's fine. Share to. So from the home of the page, you want to go to live sessions.
Live sessions, yes.
And at the bottom you have recordings and resources.
Yes.
And here you have a
On
link
top
to
of that, right? Okay. I just wanted to double check.
That's the link to it. Yeah.
So for every week, it will be updated.
Yes, this will be updated with week 2, week 3.
Okay. Sure. Thank you very much.
This was also where the lecture slides will be. I was going to do it during the break, but I didn't have time. We've been doing some stuff. So that'll be after this. After this, I'll try to remember to put the lecture slides up here as well.
All right. Thank you so much.
Cool. All right. So it's definitely over time. I need to give me 1 second to get the file. I've misplaced it. Okay. Okay. All right. Just double check. You guys can see the lecture slides? Yes. Okay. Cool. So this second lecture of Module 2, we're going to be covering metrics and data. So in the previous lecture, we talked about how to create the models.
Hello, you there?
Hello, is there any interruption?
Yeah, I think we lost
Yeah,
him.
Yeah.
I think we lost him. He's
Not hearing
frozen.
anything. Yeah.
He's either asleep or it's
And
frozen.
good
Oh,
that model is.
he's come back. You come back to life. I can't hear you now.
I seem to have disappeared. Okay. Where did I?
There was interruption, Doctor.
Okay. Sorry about that. Okay, so I'll recap. We are talking about metrics and data. Oh, okay. Talking about metrics and data. I'll just quickly recap. I don't know how much you got. I'll say it again. When we have a model, we want to be able to measure how good the model is. And so we need to use metrics to measure how good is the model. That'll give us a number. But unfortunately, numbers do not describe reality perfectly. And so we also need to think about how the metrics sort of don't describe reality. How, if we get a good metric, is that a good thing or is that a bad thing? So we need to talk about the data that underlies it to see whether if we measure the data, measure metrics on the data, whether that's good or not. Okay. So let's talk about those metrics. Why do we need metrics? Once we have a model, we need to know, is it a good model? Because we could have any parameters. We could choose any value for A and D in that 1D model, and it could be bad values. Previously, as we just saw, we sort of measured how good the model was by its performance on the loss function. So the sum of the squared error for the linear regression models. If it had a low sum of squared error, then it was a good model. But if we want to talk to other people about the model, about how good it is, maybe we don't want to use the sort of mathematical standard value sum of squared error that's good for talking about the theory. Instead, we want something that's a bit more interpretable. So instead of that number 6,969, 6,925, whatever it is, which kind of doesn't make sense, like 6,925 wrong. That's the measure of how wrong it is. We probably want to describe it in units that we're more familiar with. So if we have some regression metrics, and we think about what numbers could we use to describe how good the model was. We've previously looked at the squared error. We've gone the y minus the y hat squared. And we've also looked at the absolute error, the y minus the value minus the predicted value, and we take the absolute value of that. And then we talk about aggregating them with like the mean of those values, right? Or the sum of those values. Either case, doesn't matter. It is our recommendation that you use the absolute error and probably the mean absolute error, but you could also use the median absolute error. And the reason why we recommend you use the absolute error when you're talking to other people about how good the model is because the number that comes out of absolute error has units. It's an interpretable value that has units. So let's have a look at the house prices again. If we have 3 houses where they have prices like this, 400,000, 520,000, 610,000, and we have some model that is predicted for them, 390,000, 540,000, 600,000. We can measure the absolute error of these. So this is 10,000 wrong, this is 20,000 wrong, and this is 10,000 wrong. And we can calculate the mean of that, and that's 13,333. So now since it's absolute error and it has units, this actually means that the average prediction is $13,000 away from the true price. And that becomes very interpretable. We know what that means, right? If the model predicts a value, probably it's going to be about $13,000 wrong. So we recommend that you use the absolute error, the mean absolute error usually, sometimes the median absolute error. But you could report anything. You could report the squared error, and that would be a legitimate way to describe the model. There's also another metric that we use for regression, or people use for regression, called R squared, which is another measure of how good the model is. Often, especially in research, we will report many metrics because we'll report multiple. We'll report the mean squared error, and we'll report the mean absolute error. These tell us different things about the model. Each metric is telling us something different, and so we might want to report multiple metrics. And if we report multiple metrics, it gives us a more complete picture of what's going on. But again, if you're just going to choose one for regression, I highly recommend using absolute error because you get this nice interpretable answer. Okay? But that's regression. That's kind of easy because, as we saw, the regression metrics are very similar to the loss function. They're just a measure of how good the model is as a number. We've seen how to calculate that. A little bit more complicated is classification. Now, we didn't talk about creating a classification model because it's mostly the same, but the metrics for classification are quite different. So let's talk about binary classification. In this lecture, we're going to be talking about binary classification. In a later lecture, we're going to be talking about multi-class classification. So binary classification is when there's only two possible classes. Multi-class classification is when there's more than two classes. We're just going to focus on the simpler case. There's only two possible classes. And usually when it's binary, it either is something or it isn't something. Okay. In this case, let's think about it is a mushroom or it isn't a mushroom. So we have two images, and we're going to say we can predict whether it's a mushroom. Either it is a mushroom in the image or it isn't a mushroom in the image. Two possible classes, but four possible results when you make a prediction. Okay, so in the top left, we have the image is of a mushroom, and we might expect that a model might easily be able to identify that there is a mushroom in this image and would predict that there is a mushroom in the image. In the bottom right, we have there isn't a mushroom, and it's kind of maybe easy for a model to see that there's no mushroom, so the model would predict that there is no mushroom. And those are the two cases where the model is correct. There's actually two separate ways that the model can be incorrect when it's making its prediction. In the top right, we have a picture of something that kind of looks like a mushroom, might be a bit difficult for the model. So maybe the model predicts that it's not a mushroom because it doesn't look like the mushrooms that it's seen. This would be an error. This would be a mistake by the model. It would predict that there isn't a mushroom when actually there was a mushroom in the image. And the other type of error is the inverse, where it looks like a mushroom to the model, but it's not actually a mushroom. So this is like a costume for somebody or a statue. Not clear which way. But it's not actually a mushroom. So this is the inverse. So it's not a mushroom, but the model predicted that it was a mushroom. That's another way that the model can be wrong. And these are arranged in a particular way. You'll notice that the top two images are pictures of mushrooms. It's a Doctor Who character, okay. And the bottom two pictures are of things that are not mushrooms. And then separately, looking at the columns, the first column is when the model has predicted mushroom. And the second column is when the model has predicted not mushroom. And these 4 spots are the only 4 possible outcomes when a model makes a prediction for binary classification. So all of our metrics are based on counting how often did each of these 4 possible outcomes come to pass. So usually what we'll do is we'll measure these things, we'll show these things in what's called a confusion matrix. It is, in this case for binary classification, it is a set of 2 by 2 numbers, integers, counts of how often that situation occurred in our dataset. We give these positions in the confusion matrix very specific names, and it will take a little bit for you to get your head around it. You will have to see it maybe 10 different times and several weeks of having it in your head before you'll sort of get it in any kind of sense that you'll be able to describe it. But I'm going to describe it here, and then you'll probably just have to repeat looking at it again and again to get this to sink in. But as briefly as possible, the name consists of 2 words. The first word is either true or false, and the second word is a positive or a negative. The first word indicates whether the model did the right thing. It's true if the model did the right thing. It's a false if the model did the wrong thing. So it's true when the model, let's look at the top left. When the model predicts that it's a mushroom, and it is a mushroom, the model got it correct. That was a true thing. The model predicted correctly. In the top right, false, negative. We'll talk about the positive, negative, but the model got it wrong in this case. The model predicted that it was not a mushroom, but actually it was a mushroom in the image. Right? So that's false. The model got it wrong. The second word is the positive, negative. You'll notice, with the positive, negative, this is deciding whether it was the positive class or it was the negative class. So the positive class is a mushroom and the negative class is not a mushroom. So we can see on this matrix, this confusion matrix, the positive and negative just refers to the column, right? Just refers to, looking back at our images, right? What did the, hold on. Yeah, what did the model think? See, I have to double check it every time. What did the model think? In the first column, the model thought it was a mushroom. That's the positive. It thought it was a positive. The second column is the negative. The model thought it wasn't a mushroom. And that's the second column. And so you can see the positive, negative is just the columns. The true, false is not the rows though, right? Because it's deciding whether the model was correct or not. So if we have a look at a false positive using that knowledge. So that's just one we haven't looked at. A false positive. Let's use this to have an English sentence to describe what a false positive is. The English sentence is, it's a false, meaning the model got it wrong, positive, meaning the model thought it was the positive class. So a false positive is when the model thinks that it is a mushroom, but it wasn't actually a mushroom. It's false, right? It was wrong about predicting that it was a mushroom. Let's use the same logic on the false negative. Okay, so it's a false negative. It's a negative, meaning the model predicted that it wasn't a mushroom, predicted a negative. And it's false. The model was wrong about the fact that it wasn't a mushroom. True positive, the model predicted that it was a mushroom, and it was a mushroom. And a true negative, the model predicted that it wasn't a mushroom, and it was in fact not a mushroom. As I said before, these are the only 4 possible cases that we can have when a model makes a prediction for binary classification. So every single example, if we have a series of images, we have a whole image data set. What we want to do is go through the data set, and for every image, we're going to decide, is that image a true positive, a false negative, a false positive, or a true negative? And for every example, if it is a true positive, we add 1 to that spot. If it's a false negative, we add 1 to that spot. And we go through a whole data set and we end up with a count. How often was it this? How often was it that? And so here's an example. In this data set, the model predicted that it was a mushroom, and it was a mushroom 950 times. The model predicted that it wasn't a mushroom, but it was actually a mushroom, and it was wrong 50 times. The model predicted that it was a mushroom, so the model predicted that it wasn't a mushroom over here 50 times. The model predicted that it was a mushroom, but it wasn't actually a mushroom 120 times. The model predicted that it wasn't a mushroom, and it actually wasn't a mushroom correctly 5 times. So we're going to use this to calculate some metrics about how good this model is, starting with the most obvious one, which is accuracy. How often was the model correct? Out of all of the images, how often was it correct? To calculate accuracy from this matrix, we go true positive plus true negative divided by everything, right? All of them, the true positives, true negatives, false positive, false negatives. So this is just the proportion that it was correct over the total number of examples. And in this case, that comes out to be 84.88%. However, let's have a look at this. Let's have a look a bit more at this. Let's look at the negative case. So if the image was not a mushroom, it got it wrong 120 times, and it only got it right 5 times. That's really bad, right? If we only look at this one, there's 125 cases, and only 5 of them were correct. But the accuracy, the overall accuracy was almost 85%. So there's this sort of mismatch between what the accuracy is telling us and what if we look at this, what is telling us if we just look at this one column. So this is why accuracy isn't the only classification metric. We also have to measure we have other metrics to capture this kind of thing that happens. And the reason why this has happened, why this is misrepresenting how good the model is via accuracy, is because there's an imbalance between the number of images in each case. There's 1,000 images which are mushrooms and only 125 images which are not mushrooms. And accuracy can start to not tell us the right information. So we have other metrics which aren't as affected by an imbalance. One of those metrics is precision. Precision, we'll look at the formula in a moment. Let's look at the English description for precision. Out of all of the examples which were predicted as the positive class, how many were predicted correctly? Out of all of the image predicted as the positive class, so this column, these were all the ones that were predicted as a positive class, how many of those were predicted correctly?
From the outside.
Who was talking? I muted them. So let's look at the formula now. The formula for precision. Let's look at the bottom part. Out of all of the examples predicted as the positive class, that is the true positives and the false positives. All of the positives, right? True positive, false positive, all the positives. Out of all of them, how many were correct? How many were the true positives? How many of the positives were the true ones? So we can calculate this. And the precision of predicting that it's a mushroom is 88%. That's pretty good as well. You'll notice that there's sort of a symmetry here, though, right? This is talking about the positive class. We could also talk about the negative class. And so we would then do the same thing, but for the negative class, okay? We can also look at another metric called recall. And this says, of the examples that actually are the positive class, how many did the model predict correctly were that positive class? This is distinct from the precision because the precision we look at how many out of all of the times that the model predicted that it was positive, we calculate something. And then for recall, we're looking at out of all of the times that it actually was a thing, not dependent on whether the model predicted it was correct or not, right? For the bottom part of this. And so where the precision looks at this column and takes the number that was correct, it takes the proportion that was correct out of this column, the recall is the proportion that was correct out of this row, right? We're talking about all of the image that actually were a positive class, in the case that were a mushroom. And so we're looking at the proportion of this row, which was the correct ones, the true positives. And same deal, we have that symmetry. And so if we only look at the positive class, we get these really nice high numbers of accuracy 85%, precision 88%, and recall of 95%. But if we looked at the negative class, then we would see different numbers for these, right? Different precision, different recall. And it would be a bad. And the example I gave before for the recall, right? For the negative class, what is the proportion of the negative class which was predicted correctly? It was 5 out of 125, right? But now we have these extra metrics. We have precision and we have recall, and they're kind of like it's kind of annoying to have more than one metric because how do you know if a model is good? Do you measure on precision or do you measure on recall? If we can, we would like to have one number and only optimize on that one number. And we've already said accuracy is kind of out for unbalanced data sets. So we have these two metrics. So how do we handle that? We could take the average of them, but mathematically it turns out that kind of doesn't do what we want for complicated mathematical reasons, which, to be honest, I'm not 100% certain on. I'm following what everyone else has done. We use a different kind of mean. Instead of just adding them up and taking the average, we have another kind of mean called a harmonic mean. And this is related to the fact that they sort of you want to multiply them together to get a result. Doesn't matter. This is just what we use to take the average of these ones. It's called a harmonic average, a harmonic mean. And the formula goes like this. It's 2 times the precision times recall divided by the precision plus recall. Or if you want to define it just in terms of these true positive, false negatives, it's 2 times the true positive times 2 times the true positive plus false positive plus false negative. Something you'll notice about this is that the F1 doesn't include the true negatives. Okay, so the F1 is actually dependent on the class. So you have F1 of predicting that it is a mushroom, but you could also calculate F1 of predicting that it's not a mushroom. But for this, we'll just look at predicting F1 of predicting that it is a mushroom. And when we do the multi-class classification metrics, this is going to be, we're going to go through that in a bit more detail, looking at it in multiple different ways, right? Having the F1 for different classes. So for now, we're just going to be looking at the predicting for the positives. So this F1 score, we use it when the classes are a bit imbalanced. And you might think like, okay, so what if the classes are balanced? Could we use F1 score? And you can, because it takes a bit of thought. You look at the formula, but you'll eventually see that if the data set is exactly balanced, that we have the same number of positive cases and negative cases, then F1 is exactly equal to accuracy. But as it becomes more imbalanced, F1 sort of deviates from accuracy, and accuracy can be sort of often will be less valid. So we would tend to use F1 score. Choosing the right metric, because we've we've actually got a few, right? We've got the accuracy, we've got precision, we've got recall, and we've got F1. So which one should you use? It'll depend. Even in unbalanced data sets, sometimes you do only care about the accuracy. The That's it. That's just the average overall. How often will it work? But this is commonly the case that you actually care about precision or recall more than you care about accuracy. So if you want to make sure that the model doesn't predict the positive class incorrectly, that is, we want to avoid false positives more than we want to avoid false negatives, we should be looking at the precision. If the model is predicting, so if we're looking at a medical test to say whether you have a disease, depending on the test, if it's costly to get that wrong, you would have to go through a bunch of tests and they would have to do biopsies, costly to get it wrong. Then we want to avoid the false positives and we want to make sure the precision is as high as possible. And we kind of don't care as much about the other parts. Recall is the opposite. If we care about false negatives, so we don't want to miss anything, if we're screening for something, we want to make sure that the model doesn't miss anything. We want to calculate the recall. But if you don't know, if you're not sure anything about your data, the default, I think, that you should choose is F1. It's an average of the precision and recall. It handles unbalanced data a bit better. It's not the only thing you should use, but I think it should be a default. These are sort of reasons why to choose them. Perhaps you report all of them. Those are the metrics. Now, let's talk about the limitations of those, right? So we've talked about calculating it. We've seen the nuts and bolts of how to actually calculate it. And we get a model and it tells us that we got a model that's 90% accurate. What does that mean? Well, it means that for the data that we collected, in the abstraction that we chose to use, the model got the answer that we hoped it would get 90% of the time. However, metrics themselves have fundamental limitations. When we use a metric, we are describing the world using numbers. We do this a lot. This is a common thing that we see. So statistics, we love to use our statistics to describe reality of what's happening. So we might see education is said that it was successful if test scores go up. That's a metric. We can say a business performed well if it got a lot of dollars in profit. A technology is environmentally friendly if it has low carbon emissions. These are numbers that we apply to things in order to get a sense for what it is in reality that means, right? If the carbon emissions are lower than other things, then that's better, that's good. But reality is more complex than just the numbers, right? Education policy that improves test scores can sometimes encourage bad behaviors. We can have teachers teaching to the test. So we're not focusing on a well-rounded education, we're focusing on students who can get a high score on a test. There's correlation between getting a high test score and being an educated person who is well-rounded and knows things and is able to navigate the world better, but it's not the same thing. There's a gap. So for every metric, there's a measurement gap. There's a gap between what we measure and the real world. When we're looking at these metrics, it's very important that we keep in mind this measurement gap. We've measured something, we've got a number, but that doesn't make it objectively true about the real world. It just means that the data we've collected is telling us something. It's giving us evidence for something in the real world. But there could always be something that's different, and there might be some unexpected reasons why the metric is high, but the model is bad. So we always have to keep an eye out for that. And on that point, that's what leads us into talking about the data. How do we get ahead of this? We want to make sure that when we train a model and we get some metrics, we can trust it. Because if we can't trust the metrics, if they're not really telling us about reality, what's the point in calculating the metrics? So remember, we're going to take a step back now and we'll answer that question in a moment. Remember that our machine learning models are learning from the data. Think about how we learn about things. we have our mental models, which are based on our prior experiences. The machine learning models are based on the data that we give it. If we are told misinformation about something, we're going to learn something that's wrong about the world. If our data that we give to our machine learning models doesn't reflect the real world properly, then we're kind of lying to the data. We've got misinformation to our model. And even those metrics, which are based on the data, will start to diverge from reality. Remember that our machine learning models, they start from nothing and they're told how the world works by the data. They can't use common sense. They don't have the underlying world that they have interacted with to get that common sense. They are much more susceptible to this kind of misinformation in the data than we are. And humans are fairly susceptible to that. So we need to make sure that we have a good data set and we have a model that works well on that good data set. Good data set is a data set that represents the world correctly. It accurately represents the world. And because our machine learning models are dependent on the data set that we give it entirely, it's not using any past other experiences. If we come across some new data, we've got decades of learning of our life to draw upon to make sure that we are interpreting that new data in a certain way, and a way to match it with the rest of our understanding of the world. Machine learning models don't have that. So the ability of a machine learning model to be good and properly work in the real world is dependent entirely on exactly the data that we use and how well that data represents reality. Not only that, I'm going to skip that one. I'll talk about that in a second. And see if I can go here. Not only that, what we do in machine learning is we have an algorithm that optimizes our metric of success. It optimizes our measure of how good the model is. But there's that gap, right? And there's that problem, there's that case that the data doesn't reflect reality properly. In fact, if you have a small amount of data, you can't represent reality properly because you can't cover it. And so I'm going to go back one slide now for this. When we're collecting a good data set, we need to make sure that it covers all of the examples that the model could see. Maybe not every possible conceivable example, but has to cover the ideas that are in each that each example could have, right? So for example, with the house price data, you may have noticed that we only had house prices between, say, I think it was $400,000 and $900,000. We can't expect most models to work outside of that range of house prices if it's never seen examples from outside of that house price. For example, I talked about how the model said that a house with floor area of 0 costs $60,000. Well, that's what the model's going to say. That's not what it would be in reality. You don't have a house. If you have a house with 0 area, you have no house. It's kind of a different game, different type of price that we're talking about. So when we're creating our data sets, we have to make sure that we cover our data set, cover our space of possible things. And we usually do that by making sure our data set is a sufficient size. Okay. And yet another consideration, and this is a really big one, it's an important one we're going to probably end on, which is unfortunate because there's a few more slides here, but this is what we're going to end on. When we're using that data, that coverage, we're hoping that our data covers all of our real world. We're hoping that the data shows the model exactly what the real world looks like by covering all the possible cases. But it usually won't. And if we're using this mathematical way to minimize our metric, we're going to need a different way to assess whether it's a good model, not just that number, that metric, on the data that we've used to train it. Because we're really concerned about whether that data we've used to train it is sort of general information about the real world. So how do we fix that? What we do is we split up our data set into a train set and a test set. Our train set is used to set those parameters. That's the data that basically everything we've looked at has been train set information, train set data, where we optimize the parameters of the model and get a model, and we have that metric. We have the metric of how well the model matched the training set, and we use the labels, like the house prices that we know, in order to choose the parameters. And we have another set of data that we make sure that we never, ever use to choose the parameters of the model, or hyperparameters, which we'll talk about in other parts. There's also hyperparameters that we have to choose. So we never choose any parameters or hyperparameters for the model using the test set, because what we're going to do with the test set is we're going to say that this test set represents the general case. This is data that the model hasn't seen. This is something that the model cannot have cheated with. It hasn't been, if it was misinformed by the training set, it's going to get these wrong. And so the test set is a measure of the generalization of the model. It is how we evaluate the model. And so actually, whenever you talk about model metrics, we haven't mentioned it before, but I'm going to mention it now. We never use the test set to tune any model, because when we're telling somebody else that our model is good, we don't tell them the results on the training set. We tell them the results on the test set. We tell them, we made an estimation of how good this model will work on any data, not just our data that we've optimized it on the general case. We've used the test set to evaluate our model. So that's just something to keep in mind. Whenever you're reporting your results, you always want to report the test set information. We have 1 more minute, and so I'm just going to talk about 1 minute before the 5 minutes before, a few more minutes. The sort of most important error that we talk about from models is called overfitting. And this is where the model gets a very good metric score on the training set, but it gets a very poor metric score on the testing set. And what that means is that the model has seen the data. When it's overfitting, it's seen the data and it's gone, oh, I know exactly what the answer is. I can match that answer exactly on the training set. And it turns out that matching the answers exactly on the training set isn't actually a good model. So let's have a look at good fitting versus overfitting. What we want is a model that identifies the trend, that identifies the relationship. If we overfit a model, we have a model that gets your training data exactly correct, but anything outside of your training data is incorrect because it's been so overfit. All of the parameters have been tuned and fit to your training data a lot. So this is like the fundamental thing that the test set allows us to evaluate. Is your model like this on the right-hand side? Or is it more like the middle one, where a new data point comes in, and you can see that this line, which represents the model, it's a lot closer to this purple point, right? This purple point is a test point. Sorry, this purple point on this graph is a test point from the test set. We can see, yes?
Sorry, Brendan, can I just want to clarify regarding the test set. So test set we use to test how good the model is.
Correct.
Okay.
Yes, we use the test set to evaluate how
So
good the
we build
model
the model. We build the model using the
train set.
training set of our own parameters, and then we run the model and then compare against the test set.
We see how good it did on the test set. That's right. Because if you only measure on the training set, this is what you can get. You can get a model that has zero loss. It's perfect, quotation marks, on the training set. But it's not a good model, right? It hasn't identified a relationship. It hasn't figured out the trend of it. It's just exactly matched the training data. And so we want a model that's good in general, not a model that's good on the training data. In addition to overfitting, there's another concept which is less of an issue called underfitting. And you can see this data here. If we tried to fit a linear regression model here, that would be an underfit. And when a model underfits, that tells us that it's not a complicated model enough. It's not a model which is complicated enough to match the relationship. This is mostly an issue for linear regression and sort of a justification for why we need to use neural networks instead of linear regression. But also for linear regression, you can have something that looks like underfitting. So it is underfitting. So you can have a smaller neural network or you can have a larger neural network. And a smaller neural network might underfit. It might not have enough power. Of course, this is in 2 dimensions here. So all neural networks will be able to match this. But if you have a 1,000-dimensional situation, images are high-dimensional data, then you want a model that can find a line in a 1,000-dimensional space. And of course, that's much more complicated than what we have here. And so a small neural network may not be able to do that effectively. And here's another, so I just want to go, here's another example. We will actually end on this one. If we look at this,
Sorry,
and we say,
Brandon,
yes, Wei?
can we see the previous page?
Yes.
What is the blue point?
The
blue point?
blue point, oh, I see as purple. Okay.
Okay.
It is a test data point. So if we look at this, purple is a test in the diagram. The rest of them, they're orange here, but they're red here. So the red points are your training data, and your blue purple point is your test data.
Yeah. Good. Awesome. Thank you.
Yeah. All right. The last thing, can we identify the same thing? Which one is overfitting? Which one is matching the training data exactly, but probably wouldn't represent the trend very well?
B.
Which one seems to represent the trend reasonably well?
A.
Yes. Cool. That's overfitting. We are out of time for the rest of it. I will continue for 2 minutes to just get it down. But if you have any questions about it, maybe we can talk about it in the lab time or put it onto the LMS or send me an email, something like that. So this one is actually important. We talk about the errors in the data set. So when your data set is wrong, it can be wrong in 2 ways. It can either have a random error or it can have a systematic error. And the only thing I'll say about it is that random errors are errors that are randomly distributed. You just sort of make the same kind of mistake every time. And it can be you'll have to see it. I'll have to cover it in the lab. It's random errors. It's completely random. If it has a random error, the model can learn how to handle it. If it is a systematic error, where the model gets biased because of the way that you collected data, it's systematically causing a problem in the data collection, then your model is going to become biased based on the bias that was in the data collection. And so your metrics may look good, but your model is actually bad and it will do bad on the test set. And this is sort of the cause of model doing, one of the causes of models doing well on the train set and then bad on the test set. Okay, we are out of time. I have to move over to the lab now. I apologize for how the last part was rushed. Let me know any questions you have on the LMS, or you can come to the lab that we're going to be doing now.
Can I ask a question here
Yes,
now?
ask a quick
Are you
question before we
leaving?
go. Yeah, I think we can.
Sorry.
Yes, ask a question.
Quick one. Sorry, just regarding the assessment. I've started like I've done the Google Colab notebook and got the data set ready and everything. Just wondering if how long roughly it should take to do the quiz as an
To do the
average.
quiz, I'm not certain. I would estimate probably an hour and a half, 2 hours would be my guess, but maybe it'll be 3. It'll depend on you, of course.
Yeah, sure.
But once you've finished the sheet,
So
maybe
sheet,
that's
do
my estimate.
we need to do the sheet again? Like as I've done it last week.
If you did the collab sheet,
yeah,
that's all. If you're
Don't-
doing
don't need
the
to do it again?
assignment is a collab sheet, and you have to complete that. And then you
Don't have to
upload
do
it.
it again. Don't have to run those models
you-
or those codes again to do that.
No. Well, you do it
Just-
once. Yeah.
Just to add on that, do we have a timer once we start the quiz? Like,
Once you open the quiz will remain open until the due date is passed. So that means you can open the quiz, you can immediately close your browser, and you can come back in 2 days, and it'll be fine.
Oh, so we can do it in multiple attempts. Or like we can.
Yes.
we can
Yeah. Just don't click finish attempt. That's all. Yeah.
Okay. Thank you. Thanks, man. Good night.
I will upload the PowerPoints. I will.
Thank you, Brandon.
Thank you.
Write myself. All right. Thanks.
Thank you.
Thank you. Bye.
See anyone who's coming to lab in the lab.
Coming.
Yeah, coming.